Hello everyone. So today we'll be determining the resolving power of a telescope and we'll compare it with a theoretical value which we will determine using formula. So what we need is we need a sodium vapor lamp which we have kept over there, and we also need a telescope, and we will have this to take the readings for the telescope, and we need a measuring scale. That is this way. So these are the adjustable slits and everything, and the object is kept there, which will be viewing on the sodium vapor lamp. So, according to the resolving power, so resolving power of a telescope is nothing but its ability to resolve two closely lying objects. Okay. So, using this formula where A by 1.22 lambda equal to D by D, will be able to find what is we can actually compare the theoretical value and the experimental value. Here, A is nothing but A1 plus A2 divided by 2. I'll be telling you what is A1 and A2 in a while. Okay. So what you do is first we will do the initial adjustments which we need. First we'll calculate the pitch of the scale. As you can see, this is the scale which we need. This scale is called the pitch scale, and this scale is called the head scale of the telescope. So using this pitch scale, as you can see, I've kept it exactly at 0. The pitch scale reading will be taken from this line which is below. As you can see, there's a line below here. That will be the pitch scale reading taker. So this is the pitch scale. I've kept it exactly at 0, and I've kept the head scale also at 0 here. Now, I will give 5 rotations to this. 5 rotations in the sense you just move it in this way. 1, 2, 3, 4, and 5. I have shifted the head scale 5 times. So as you can see in the pitch scale, we have moved 5 divisions altogether. Okay, so the pitch scale reading is here and we have moved 5 divisions. So we have moved 2.5 divisions, as you can see here. The line is here, okay, and it is exactly in the middle. That is 1 to 2.5. Okay, this is the reading. So now we can write. So the distance moved on the pitch scale is 2.5, and we have given total 5 rotations. So it's going to be 0.5 mm. The pitch will be 0.5 millimeters because it's in millimeters. Now the least count will be nothing but the pitch divided by total number of head scale divisions. So total number of head scale divisions here is, see, as you can see, 90. This will be the 100th division. So total head scale reading is 100. So 0.5 divided by 100 gives 0.005 millimeter. This is the least count. So now we know the formula TR, that is the total reading is equals to pitch scale reading plus head scale reading into least count. So now we'll start the experiment. You fit this telescope, you fit the scale in such a way that you will be able to rotate it properly with your right hand, and you can see the slit through. Okay. So as you can see in the initial condition, the slit will be well separated and it will be bright enough. Now what you do is, see through the telescope, you will adjust the pitch scale in such a way that you will decrease the length like this. Yeah. You will decrease it in such a way that the two slits, the line between the slit decreases and the two slits appear to be just real. So initially it will be at this condition, that is the two slits will be open wide and you will be able to see two distinct slits. Just resolved will be in a condition where you will be able to see only thin line between these two objects, but you'll be able to differentiate the objects. Then just close is, as you decrease, as you close, as you try to close this, it will become black. So now in the just resolved case, you have to take a reading. The pitch scale reads 0.5 here because it is near, it's in between 0.5 and 1. So it is, take it as 0.5. You should take always the previous reading. Okay. And as you can see, it is more towards the 0.55. So the PSR reading will read less than 50. Okay. So the HSR reading will read less than 50. So as you can see, it is exactly at 30. This line is merging with 30. So we can take the PSR as 30. We can see PSR as 0.5. HSR as 30. Using this formula, we can write it as 0.5 plus 30 into 0.005. Okay, so you'll get it to be 0.515. Okay, So this will be 0.5515 millimeters. Okay. If you convert it into meters, it is 10 power minus 3 meters. That's it. So this is for A1. This is A1. A1 is nothing but the total reading at just resolved case. We'll fix the telescope again. And what we'll do is we'll increase it even more until the immediate point where it will just become black, entirely black. You will not be able to see the object at all. So that point will be the. So as you can see, this would have decreased, and we can see it has moved here. So it is between 0 and 0.5. So we can take it as 0.5. So we can take, sorry, it is between 0 and 0.5. So we can take it as 0. And we can see it is more closer to the 0.5 line. So it will be nearly 50. So as we can see now here, it is 47. Okay. So the 47th reading. So we'll calculate, this is A1 we have calculated. Now we'll calculate A, which is 0 plus 47 into 0.05. 005. So it's 0.235 into 10 to the power minus 3 meters. So if you add these two, you basically don't add these two. What you do is you just take the difference. A1 minus A2. It should be positive. If it's not, if it's negative, take the modulus. That's fine. So it's A1 minus A2, you will get the answer. So 0.515 minus 0.235, you get it around 0.3 meters. Then you apply the formula A by 1.22 lambda. A is nothing but what you have found, A1 minus A2. Lambda is nothing but the wavelength of sodium, that is 560 nanometers. Convert it to meters and you can do it. And then D by D. The D is constant. D is not, the small d is nothing but the distance between two slits, which is 2 millimeters. That is 2 into 10 to the power minus 3 meters. And the capital D is the distance between the object, the telescope, that is this. The distance between this and the object slit. So you will maintain this distance for you'll vary the distance and then you will be repeating the experiment again. So as we can see here, initially you will be doing this. You will be setting the distance first between the telescope and the object, and then taking the.
What's the minimum approximate to do it? Minimum approximate.
You always take the readings above 1 meter, because then you will be able to easily identify, you will be able to easily get this one. It will be equal. The values will be approximately equal. That's okay. So take it 1. We'll start with 1.3, 1.6, and 1.8. You can do it, but based on the table length, you cannot be able to take that. Okay. So now I kept 1 meter. And I've taken another 20. So it is 1.2 meters. So 1.2 meters from here till here. This is the length. So this is the distance. Capital T will be this, that is 1.2 meters. And small t will be 2 millimeters. That is always constant. That is the distance between these two slits will be 0.2 meters. 0.2 millimeters. 2 millimeters. So now using that formula, the theoretical value, that is D by D, and the experimental value, that is A by 1.22 lambda, should be almost similar. Okay, should be almost similar. Then you have done the experiment correctly. And this is how you do resolving power of telescope.